Hi, it's time for some more calculus. Let's do this thing. Woo woo! We're going to be doing daily lessons 151 and 152. There we go. I got this. And this is all about optimization. So let's do this thing. So optimization is how do we optimize something in a problem. It could be optimizing the area that something covers. It could be optimizing the volume. It can be optimizing the space, whatever we are using. That's the area again. But we're optimizing or in some ways minimizing. So we're either finding the most or the least of something in a real world problem. So let's do this thing. Okay, so when we get to these optimization problems, we're going to draw or write down what we need. I play with this problem a whole lot where I'm going to be circling things and underlining and whatever, but we draw and write down what we need. Then we set up a constraint and optimization equations. So there are going to be some limitations of a problem. So let's say we're talking about, we want to figure out how much we want the most volume that we can fit into a can, but the least amount of surface area. We figure out how exactly do we do that. We can solve the constraint to plug into the optimization equation. We'll do that in a minute too. Use the optimization equation to find critical points. So this is how we find relative min, relative max. And then we answer the question and check yourself. So meaning we just see, does this answer make sense? And you're probably saying, this whole thing doesn't make sense so far. I have no idea what you're talking about. So let's just get into it right away, and we're going to start by doing problems. That's how you're going to learn about this. So here's an example. A manufacturer wants to design an open box. Okay, so right now I'm just getting this in my head. This is an open box, having a square base and a surface area of 108 square inches. So if I'm thinking about a box in some way, and it has a square base, and it has a surface area of 108 square inches. Okay, great. So somewhere over here, I'm going to write surface area is 108 square inches. What dimensions will produce a box with a maximum volume? Okay, here's where you're really diving in and you're like, the maximum volume. This is what I'm going to be taking the derivative of. Whenever I want to find a maximum value, I take the derivative and then I set up some sort of chart where I figure out where does the derivative, in the case of a maximum, change from positive to negative. In the case of a minimum, change from negative to positive. I'm still doing that same thing now. I'm still using all the calculus we learned up until this point. So I'm saying produce a box with a maximum volume. What is the maximum volume? Okay, because I know I want to take the derivative of volume, I have to think of what is that equation. So we were talking about an open box. So just an open box, I'm going to say is length times width times height. But in this particular problem, we can say, well, hold on, a volume, in this one it says it has a square base. So instead of length times width times height, two of these measurements are going to be exactly the same. I'm going to get rid of this L because I don't like writing L's in equations. And now I have W times H. If I simplify that a little bit, and you might be thinking right now, there are still way too many variables in this. I don't want to do some sort of crazy related rate problem. I just want to get this down to one variable so I can take the derivative nicely without doing a bunch of related rate stuff. So I've got V is equal to W squared times H. And so what I'm going to do now, knowing that I still want to take the derivative of this, I'm going to see, is there something I can do to make it easier? Well, right now, I know that the surface area of this box is 108 square inches. This is a constraint on the problem. I can't change that. So I'm going to say, if surface area is 108, well, how do I find surface area? So if you think about a box, this is going to be really good. No, this isn't, I didn't just sit a box on this page. Like, this is actually just something that I drew. And let's say this bottom is W and W, and then we've got height. So this is where the W squared times H comes from for the volume. If I want the surface area, well, a box has 1, 2, 3, 4, 5, 6 faces. So I'm going to say all of these faces I need to add up somehow. Well, I can see this one over here is going to be WH plus the one on the other side is WH. Hold on, this one's WH, this one's WH, this one's WH, this one's WH. So all around the outside, so all of those on the outside. So I'm going to say 4WH plus the bottom is W squared. And you might be tempted to say the top and the bottom. In fact, I just did a second ago when I was like, oh, 6 faces. But this says that it's an open box. So I'm just going to say it's equal to W squared. This is the surface area, equal to 108. And so what I want to do is, I'm not taking the derivative of this because it didn't say what is the maximum or minimum surface area. It just said maximum volume. So I know I'm taking the derivative of this guy over here, but I'm using this to help me eliminate a variable. So I'm going to solve for one of these. I can see that there's a W and a W squared. I don't really want to solve for that. How about I solve for H? So I'm going to say 4WH, subtract W squared on both sides. So I get H is equal to this whole mess. I'm going to go over here and I'm going to say volume is equal to W squared times H is 108 minus W squared. 4W. And then I'm actually going to simplify this even more. I could take the derivative right now. I could use the product rule, but that would be pretty difficult to simplify. So I'm going to see if I can simplify before I do any calculus. What if I distribute this? So I would have 108 W squared minus W to the 4th over 4W. Or I could say that volume was equal to, and then I'm going to take each one of these. Like I can say 108 W squared over 4W minus W to the 4th. 108 divided by 4. 108 divided by 4 is 27. So I'm going to say 27 W squared divided by W, would just be W. 1/4 W to the 3rd. Okay, and so now I've got all that stuff and I'm like, okay, how do I take the derivative now? Can I do that easily? Yeah. V prime, I'm going to write this over here, so I'm taking the derivative, so this is all going up here, just so you can follow your work, or my work. W prime is, or V prime, I'm sorry, because that's what I was finding, the maximum volume, that's when I take the derivative of. V prime would be 27 minus 3/4 W squared. And we don't have to do any related rate stuff because this would just be like a Y and an X, and I'm doing this all in terms of W this time, so or with respect to W. So I'm good now because I just have one variable over here. And then I'm going to say, so V prime is 27 minus 3/4 W squared. And then I'm almost done. I have to find the zeros in order to find the maximum. Add this on both sides. Multiply by 4/3. W squared is equal to 27 divided by 3 is 9. 9 times 4 is 36. Because I'm talking about an actual width, I would only use the positive value here. So I have a width of 6. If I make a chart to make sure that this is a maximum, I would say this is W, this is V prime, and I'm only going from 0 to 6 because I wouldn't want a width of a negative number. 6 to infinity. I only have one value here, so I'm really hoping this is a maximum, but let's just try. If I pick a value from 0 to 6, my favorite one, let's pick 3. And I say, or actually let's do 1. 3/4 times 1 squared would be 1. 27 minus, or I'll do it up here, 27 minus 3/4 is still going to be positive. Pick 2,000. 2,000 squared times negative 3/4 is going to be negative, plus 27 is still going to be negative. Yes. V does have a max. And then you just have to answer the final question. So in this question, it says, what dimensions will produce a box with maximum volume? So we know the dimensions. I'll write that down here. We know right now that W is 6. So if I go up here, I'm going to have 6. And what's this say? This said square inches to begin with. So I'm going to say 6 inches by 6 inches, because it was WW. And then H by. In order to find that, I'm going to say, where is my H? We said that H, oh there it is, H is 108 minus W squared over 4W. So I'm going to say 108 minus, this would have been 6 squared over 4 times 6. And I get 3. This is the dimensions. And then it says, what's the maximum volume? Let's do that next. The volume would be 6 times 6 times 3. 6 times 6 times 3. And it just happened to work out that this is 108. It's not always. Inches. And then if I think about inches times inches times inches, cute. Whew. That was a lot. But it's not too much different. So the new stuff in here is that you have to set up the original equation and figure out, what are you finding the maximum of? What are you taking the derivative of? In this case, it was the maximum volume. That was what I needed to derive. And you need to use constraints. So another equation, like in this case H, in order to help you do that, in order to eliminate a variable to get to the point where you can take a derivative. Let's do more. Okay, there's 3 examples on here. Hopefully a little bit quicker than the last one. Example 3 is really not. Okay, a box is to be built from a rectangular piece of cardboard. Oh man. I'm going to cut out this part of the video. I'll be right back. Okay, let's start another example. So in example 2, a box is to be built from a rectangular piece of cardboard. So in here it says that it's 25 centimeters wide, 40 centimeters long. Okay, good, we got some info. By cutting out a square from each corner and then bending the sides up. I'll do that in a second. Find the size of the corner that will produce a container that will hold the most amount of soup. I really like that, the most amount of soup. And so if I'm thinking about this, what is an amount of soup? One that's really funny. This is volume again. This is what I want to get the most of. So I'm finding the maximum volume. Volume is the thing that I'm going to take the derivative of. So somewhere in here I'm going to say volume, that's the thing that I want to take the derivative of. Okay, now let's see what they're actually talking about. So in this, I'm actually going to make this smaller so you can kind of see this and I can use this paper. Okay, so even smaller than that. I haven't used this before like this, but I want to see. Okay, so it says a box is to be built from a rectangular piece of cardboard. So let's say this is my cardboard and it is 25 centimeters wide and 40 centimeters long. By cutting out a square from each corner and bending up the sides. So what happens is we actually take a square, and I'm going to do this, and it should be the same size square from each one, but I'm just going to do it like, I'm going to eyeball it. It's going to be a really good square. Okay, so that doesn't really look like a square, but whatever, you're going to get the idea. So I take a square out of each corner, and then I can bend up the sides. And suddenly, it's a box. Ta-da! It's an open box. Why you would put any soup in this, as opposed to the most amount of soup in something like this, is beyond me, but maybe you have something really, really nice to hold the sides. And they do have boxes of soup now, but this one is totally open, and that's where we're going to be putting our soup. Whatever. How I'm going to draw this, it's like that. So if I have one of these, so if I have a rectangle, and I cut out a square from each corner, I'm spending a lot of time on setup so that the problem itself becomes easier. And then I know that this was 25 centimeters wide and 40 centimeters long to begin with. So this entire side was 40 centimeters. This entire side was 25. But if I just want to know what this distance is, so from there to there, so this distance from here to here, do you see how if this whole thing used to be 40 with the corners in, how I took out a length here and then I took out a length here? Well, in this, I would say that we're cutting the square out of each side, and theirs probably is going to be a little bit more accurate than mine, that I'm cutting out the same length on this side. So let me just call that X as on this side. So this little guy is X, this little guy is X over here. Same thing on this one. This is X, this is X, this is X, because squares have all the same sides. That every one of these sides of this square is going to be just an X. So if I want this length from here to here, this is going to be 40 minus an X on this side and an X on this side. 2X. The same deal on the other side. This was 25, but if I just went from here to here, it's going to be 25 minus 2X. And then we said that this thing was X. Okay, so if I want volume, and I know volume is length times width times height. So length times width times height. I need to figure out what each one of these things is. So this one, if I pull this up, we just said that this was going to be 40 minus 2X. So these are my constraints. My width is going to be this side, 25 minus 2X. And then my height, if I look at this on the side, like what is my height going to be? This is just what I cut out over here. And this was a length of X. So my height is now going to be X. The most difficult part of this problem, I think, well, setup is the first part to try to figure that out and make sure you don't put 40 minus X or something like that. The next part is actually just simplifying this correctly. So what I'm going to do is multiply this out. 40 minus 2X times, I think when I originally did this, I multiplied the X times the first term. So this was 40X minus 2X squared. I'm going to stick with that. You could use the product rule now. That would be okay. Or you can distribute and multiply a binomial times a binomial. And that's what I did the first time, so that's what I'm going to do right now. And get, oh, I'm cheating a little bit. I'm looking at old me's work. 1000x minus 80x squared minus 50x squared plus 4x to the third. And then I'm going to do one more and say volume is equal to 4x cubed minus 130x squared plus 1000x. So multiplying all this out. And the reason why I did that is because now it's just really easy to find volume, like the derivative of volume. I would get 12x squared minus 260x plus 1000. And now it becomes a problem that you've done many times before, where you're trying to find a maximum. A maximum in order to find a relative max on a graph, or in this case, it's going to be the absolute maximum also if we're talking about this type of figure, but whatever, you'll see this in a second. If I want the most amount of soup, I have to figure out what is the maximum. And so what I'm going to do is set this equal to 0 in some way. I'm going to factor out a 4. 3x squared minus 65x plus 250. Factor here. Take a moment, do that. When I factored before, what did I get? I'll do this over on the side because I did this method. If you multiply 3 times 250 together, you get 750. Add to get negative 65, two numbers that multiply. Well, this took a while, but I'm going to use what I wrote before. Negative 15 and negative 50. And then I'm going to divide by my leading, or by my a term, which in this case is 3. And I end up getting negative 15 divided by 3 would be x minus 5. And then you get x minus 50 over 3. Set this equal to 0. Because these are zeros, you could go through the work and you could say, well, this would be x minus 5, this one multiplied by 3x minus 50, and you can do it this way in order to figure out the factors. But these actually tell me what my zeros are. So you end up knowing that x is equal to 5, x is equal to 50 over 3. Then we make a chart. This is x, this is v prime. Again, I don't want I can't have a square that has negative length. So 50 over 3. And then we go through and we pick our favorite numbers. So a number between 0 and 50 over 3, what is 50 over 3? That'd be 16 point something like that. So I pick a number between 0 and 50 over 3. I'm going to pick 1. And I'm going to go to this one that was already factored. So if I do 1 minus 5, I get negative. This is positive. 3 times 1 minus 50 is negative. So negative and negative, this would be a positive value. A number between 50 over 3 and 5. Let's pick, oh man, did I just mess this up? I just said 50 over 3 was like 16 point something, and then I went to 5. Hold on, let's go back. Okay, let's try this again. So I've got these two numbers. I've got x is equal to 5 and x is equal to 50 over 3. So I messed this up the first time. 50 over 3 is going to be like 16 point something. So I put these in the wrong order on my chart, but hopefully it just skipped that part of the video for you. This would be 5 to 50 over 3, 50 over 3, 50 over 3. Okay, so we found these x values. We found the 0 to be x equals 5 and x equals 50 over 3. The first time that I did this, I actually messed it up. That's why there's a weird cut in this video. But we should be going from 0 to 5 and then 5 to 50 over 3 because 5 is less than 50 over 3. I got this. It's pretty early. I pick my favorite number from 0 to 5. I'm going to pick 1. If I pick 1, x minus 5 or 1 minus 5 will be negative. 3 times 1 minus 50 will be negative. Negative times negative is positive. And 4 is already positive. A number between 5 and 50 over 3. Let's pick 6. 6 minus 5 is 1, positive. 3 times 6 is 18, minus 50, that would be negative. And then, I don't know, 2,000. 2,000 minus 5, positive. 2,000 times 3 minus 50 is still positive. I can see right here is going to be my maximum, and here is going to be my minimum for v, because I have a derivative that's changing from positive to negative. So I'm going to go up here because I'm kind of running out of room down here. It says find the size of the corner that will produce the container that will hold the most amount of soup. The size of the corner square, there's a couple ways that you can do this, but let's do the dimensions. The size of the corner square, I would say size of the corner square would be 5, because that's what we just found out to be the max, centimeters by 5 centimeters. Okay, let's do another one. Yeah. Okay, a rectangular page. Oh, this one takes some work, so we'll be okay. We can do this. A rectangular page is to contain 24 square inches of print. Seems like a constraint to me. The margins at the top of the page and the bottom of the page are to be 1.5 inches, and the margins to the left and the right are to be 1 inch. More constraints. What should the dimensions be so that the least amount of paper is used? This is what we're taking the derivative of, but let's think about this. The amount of paper, what is that? Area. Area would be the amount of paper. So this is what I'm taking the derivative of. Everything else, we're just trying to support that plan. Like we're trying to support and trying to sub in variables where needed so that we can take the derivative of area. Okay, so area is equal to, I'm not going to just say length times width yet because I'm going to write out this crazy situation. So we've got this piece of paper, and we know the print is in here. So this is my paper, like you know how margins work. And some of the things about here, it says the margins at the top and the bottom of the page are to be 1.5 inches. So here, this is 1.5, down here is 1.5. And then it says that the margins to the left and the right are 1. And it says, what should the dimensions of the page be so that the least amount of paper is used? So if we're talking about the least amount of paper, that is actually just like the area of the print itself. So this, the least amount of paper is going to be used because it's going to be the same in here anyway. So this one, if I want the area of the print, let's actually, okay, what should the dimensions of the paper page be so that the least amount of paper is used? Actually, this would be the area of the entire paper. Yeah. And the area of the entire paper, let's call it something. Let's say that this is length times width. Okay, so we want the entire paper, so we've got different sizes of paper. We'll figure this out. The area is equal to length times width. And now I've got to figure out, like, what does that mean exactly? So, area, I'm going to keep this like this, and then figure out, well, what are the constraints? Well, I know that the area of the print has some weird stuff going on. So the area of the print, and you could also put the other one as big, by the way. Area of the big paper. Big, just so you don't get this confused. So the area of the print, this side is not going to be W anymore. This side is going to be W minus 1.5, or 1 on this side, and 1 on this side. So W minus 2. The length isn't just going to be L anymore. That was the big paper. The print is going to be minus 1.5 here, minus 1.5 here. So I have length minus 3. And I also know that the area of the print is 24 square inches. I could solve this for L or W. Let's solve this one. What did I do it for before? I'll do the same thing as before, but you could go a different route if you wanted. I solved this for W before, so let's just go there. Dividing by L minus 3 on both sides first. W minus 2. Adding 2, so I've got 24 over L minus 3 plus 2. Looks gross, but that's what W is. And so if I want the least amount of paper used, which is the area of the entire paper, I still know that W is equal to this whole mess. So I'm going to go up here, and instead of W, I'm going to write in 24 over L minus 3 plus 2. This is what I'm taking the derivative of. I want the least amount of paper. I want to minimize this. This is what I'm taking the derivative of, but I don't want to do that yet. So what I'm going to do is simplify a little bit. So the area of the big paper is 24L over L minus 3 plus 2L. And you could do a little bit more if you wanted and try to simplify in some way, or take L minus 3 to the negative first power and then do the product rule. But what I think I'm going to do instead is just do the quotient rule now and do bottom times the derivative of the top minus top. Derivative of the bottom would just be 1 over the bottom squared plus, this would just be plus, hold on, why do I have, just checking on something because here I have 3, we'll check on it in a second. Okay, so then I would have plus 2. Okay, so I just want to make sure that I'm right because I'm seeing something that I have a little bit different than before. I think I solved for another variable before. That's what I did. I'm just going to keep going with this. Ignore my old work. Okay, so I've got L minus 3 times 24, 24 minus L over L minus 3 squared plus 2. This is what this was the derivative. So I said area of big, but make sure that you actually put prime here. And then I've got to set this equal to 0 in some way. So I need to figure out where did the zeros happen in all of this mess. So I am actually going to do this so that I get a common denominator in some way. So what I'm going to do is multiply this first one times L minus 3 squared over L minus 3 squared. So I'm multiplying by some crazy form of 1. That way, when I come over here, and so I'm just writing over here because this is where I have room. This is the derivative still, and I'm just simplifying in some way so that I can set it equal to 0 and find the minimum. This would be 24 L minus 3 times 24, 72. Minus, so this is 24L minus 72, minus 24L, plus this whole mess. I'm going to run out of room. I'm just going to write this on here. Okay, so we've got area of the big. Hold on. Oh, that's why. Okay, so in this one, we've got area of the print is equal to the W minus 2 and L minus 3. Actually, when I was looking back, what I did originally is I switched the W and L. So if you did that too, if you said, you know what, I think this is width and this is length, that's okay, because a rectangle we can switch multiple ways. We can call the width and length and we can switch them. I'm just going to keep going with what I have right here. So I've got kind of a big old mess right now where I solved this for W, the area of the print, and I said W is equal to 24 over L minus 3 plus 2, and then I'm going up here and putting this in for W. A lot of the issues after this just come from algebra. So I'm going to use this piece of paper that I used before so that I can extend my work a little bit. And I'm going to continue my work over here. So the area of the big, this would have been 24L minus 72 minus 24L plus, and now I've got this thing over here, 2 L minus 3 squared is the same as L squared. Now I have to do this. L minus 3 times L minus 3 would be negative 6x plus 9. All divided by L minus 3 squared. Keep going. 24L minus 24L goes away. And now I have 2L squared minus 12x, because I'm distributing this 2 throughout, plus 18 minus 72 over L minus 3 squared. I'm just making this a little bit easier to work with. 18 minus 72 is negative 54. 2L squared plus, or I'm sorry, minus, it's minus 12x minus 54. And then I want the places where L is going to either be a critical value. So either where L makes this derivative not exist. So in the denominator, if I set the denominator equal to 0, I would say at L equals 3. Or in the numerator, where the numerator is 0. And I can see that's at L squared minus 6x minus 54 divided by 2 would be 27. Two numbers that multiply to get a negative 27 and add to get a negative 6. Negative 9 and a positive 3. Sorry, you can't see my work. And this was just L squared, so I'm good here. So I've got 2 L minus 9, L plus 3. If I'm finding the zeros of this, this would be at L is equal to 9, L is equal to negative 3. Okay, we did all of this work to find the zeros. We said that this was, we have a critical value at 3, because that's where the derivative does not exist. We have a critical value at 9 and at negative 3. We can automatically eliminate this negative 3 because we can't have a negative length. So I'm going to say that this is L, this is A prime. I'm going to go from 0, because you can't have anything less than a negative, or you can't have a negative length, 0 to 3, 3, 3 to 9, 9, 9 to infinity. Now there's zeros here, and then I want to say, okay, well, what would L be if I go back to, I can really go to any of these, but let's say this one, and we know the numerator is this. The denominator is always going to be positive. Sorry, you can't see. The denominator is always going to be positive because anything minus 3 squared is always going to be positive. So really I just have to focus on the numerator. Remember, this numerator is the same as this guy down here. So I'm going to look down here to see whether positive or negative. A number between 0 and 3 would be 1. 1 minus 9 is negative, plus 3 would be, or 1 plus 3 is positive. This would be a negative. 3 to 9, pick my favorite, I don't know, 5. 5 minus 9 would be negative. 5 plus 3 would be positive. Negative times positive is negative. 9 to infinity, if I pick something from there, so 10. 10 minus 9 is 1. 10 plus 3 would be positive. So I have negative to negative, which means nothing. There's a horizontal tangent at 3, but that's about it. Actually, in this case, not even a horizontal tangent, because didn't we say at 3, that's where A prime does not exist. And then over here, negative to positive, this is where I've got a relative min. Okay, so all of this work just to come up with, yeah, L is equal to 9. Woo, we did it. Let's see if we answer our question. What should the dimensions be so that the least amount of paper is used? Well, the dimensions then for L, we know is going to be 9, we just said. So 9 inches, because that's what I was given in, by, And then we have to figure out, well, what's W? We know W was 24 divided by L divided by 3, or L minus 3. L minus 3, 9 minus 3 is 6. 24 divided by 6 is 4, plus 2 is 6. So even though I actually ended up switching my W's and L's and all sorts of things and doing this work totally different than I did in the past, you still get exactly the same answer. I'm just doing this just to show you that, yeah, even if you do it some other crazy way, still get the same answer. Okay, one more problem. A rectangle is bounded by the x and y axis, and the graph of y is equal to 3 minus 1/2 x. What length and width should the rectangle have so that its area is a maximum? Okay, area is a maximum. Let's think about what this is. Area is the thing that we're taking the derivative of. Area is the thing I want the maximum of. That's the thing that I want the derivative of. Everything else is just supporting in this. Area is usually written as length times width, but we're in a graph. And I know this is the x, like I'm on the x-axis here and the y-axis. So I'm going to say x times y. This one is so much shorter than the last one because I don't want to take the derivative yet because there's an x and a y over here. But I know that y is 3 minus 1/2 x. Area is equal to 3x minus 1/2 x squared. Take the derivative. A prime is equal to 3 minus 1/2 times 2 is 1x to the first power. This is so much easier than the last one. If we set this equal to 0, we get x is equal to 3. Let's make sure that that makes a prime a maximum in this case. So in this one, I'm going to say from 0 to 3, because I can see that x is positive in some way. 0 to 3, 3, 3 to infinity. I know at 3, a prime is equal to 0. Substituting a value from 0 to 3 into a prime. So if I put in 1, for instance, 3 minus 1 is going to be positive. If I put in 10, 3 minus 10 is going to be negative. That means a does in fact have a max. And so if I want to know what is the length and the width, I know that x was 3. But what should y be? Well, we know y is equal to 3 minus 1/2 x. Y is equal to 3 minus 3/2. Y is equal to 3 minus, instead of 3/2, I'm going to think about it as 1/2. That means y is, I wrote that weird. 3 minus 1/2 is just 1/2. Or I could have said this was 6/2 minus 3/2, which would be 3/2. Whew, that was a lot. Okay, thanks for sticking with me. I think you're great. More optimization tomorrow. Okay, bye.